Hello, everyone. Welcome back. Today we're going to go over section 5.5, which is applications of exponential growth and decay models. So in section 5.1, you might recall that we got familiar with using the following formula, P e to the RT, or PERT. And the problems that we did using this formula had to do with investing money. You let a certain amount of money, called a principal, sit in an account for a few years, so T is in years, and with a certain interest rate, a percentage that's converted into a decimal, then this is how much money, A is the future value of money, that would be in the account, as long as the interest is compounded continuously. So this was the model we used for continuously compounded interest. P e to the RT, or PERT. So a lot of times we would want to know how much money will be in the account after a certain number of years. Now, this particular application, letting money sit in an account and grow, uses this exponential function, e to the RT. Well, as it happens, this exponential can be expanded to include other types of applications, namely things like population growth, radioactive decay, growth of bacteria, anything that can grow or decay using an exponential, or what we say is exponentially, then you can use this model. But in this section, instead of using PERT, because P kind of is associated with principal, which is a money thing, they kind of adapt this formula to look like A equals C e to the KT. So instead of P being a principal amount of money, C, it represents an initial quantity of something. That could be an initial quantity of money, like P, or it could be an initial population, initial substance of material, mass of material, whatever, but it's an initial quantity. Now, K is analogous to the interest rate, but instead of an interest rate, we can think of K as being the growth rate. And it's also called the constant of proportionality. So this formula is the same exact thing as PERT, but they're changing P into a C and R into a K. This is what we use to model exponential growth of anything. That could be money, that could be population, whatever. Now, we have to go over some terminology here. For exponential growth, meaning anything that this model, C e to the KT, can be applied to, that means that the quantity is growing or increasing at a rate that is proportional to the initial amount present. That is, it's increasing exponentially. Now, K, as I mentioned, is called the constant of proportionality, but really it's the growth rate and is analogous to the interest rate R in the PERT formula. Now, on the other hand, you do have something called exponential decay. Not everything always goes up. Like in the context of money, we put money into account and it grew exponentially in the account, but not all models represent growth. There is something that we call exponential decay, which is instead of something getting bigger over time, it's going down over time. So anytime you have a quantity that declines or goes down at a rate proportional to the initial amount present, that is said to decrease, decline, or decay exponentially. So you can use these three words interchangeably. Decay means decline, which means decrease, but it's going down in this exponential sort of way. And the model then, instead of having A equals C e to the positive KT, it's e to the minus KT. So when we are doing word problems, we have to figure out which model do I need to use. Do I need to use the exponential growth model, which is C e to the positive KT, or do I want to use the decay model, which is C e to the minus KT? Now, the rest of this we'll come back to as we need it. So let's first get started with our practice problems and come back to any terminology that we need a little bit later. In problem 1, it says a population of wolves grows exponentially at a rate of 5.5% per year. The population was 7,100 in 2008. Now, part A of this says find the exponential function that represents the population t years after 2008. So when they say find the exponential function, they mean build the model, put all of the variables in the formula. So first you have to figure out which model do I want to use. Do I want to use the equation that talks about exponential growth? Or do I want to use the formula in the equation that talks about exponential decay or decline? So we have to pick which is the formula to use based off of the context of the problem. And part A, when they say build the formula, they mean just find and plug in the numbers that you know. Plug in C, plug in K. So let's first figure out which one of these we need. It says that the population of wolves is growing exponentially. That means that I should use the growth model, CE to the positive KT. And when it says, write the function, they mean plug in C and plug in K if you know them. Now, K is analogous to the interest rate R when we were using the money PERT formula, but K represents just the growth rate. And in this case, K is 5.5%, which you should change into a decimal by dividing by 100. This turns into 0.055 is the value of K. Now C represents an initial quantity of some kind. In this context, it would mean the initial population of wolves. So when we start keeping track, it says the population was 7,100 in 2008. So C is the initial population of wolves, 7,100. But we should note that this corresponds to 2008. So what we do is we make a note that t equals 0 corresponds to the year 2008, and that's where our timer stops. The t goes up every year after 2008. So let's put our values in our formula. We have 7,100, e to the k t, and this is the model or the function that represents the population at any t where we started at 2008. Now, this is something that you will typically have to do to start any problem. They won't write it as part A. The initial step is always build your model, and then the real question is asking you to do something with that model. So in this line, we put our growth model together, plugged in all the information we knew, and now the real questions start here, where it's asking me to do something with that. So let's read part B. What will the population be in the year 2018? Round up to the nearest whole animal. And when you're reading these, you have to determine what it is they're asking for. Are they asking for a time? Are they asking for an initial population? Or are they asking for a future value of the population? When it says, what will the population be? They're asking you to find a future value of the population. And that represents A. When you're using PERT, A was a future amount of money in the account. In this context, A represents a future population of wolves. So if they want to know what will the population be, they basically want you to punch out what A is. And if they want you to punch out what A is, that means that you've got to have a T to plug into this formula to get A. Now, what is the year that they want me to find? They want me to find the population in 2018. But you don't plug in 2018 for T. We've got to figure out what T value 2018 corresponds to. So if T equals 0 represents 2008, then 2018 is 10 years later. So T would be 10 in this case. So to find A 10 years later, you plug in 10 for T into my model up there. So for this, we're going to get out our calculator and punch it out. 7,100 e to 0.055 times 10. And we get 12,306.09. Now, in these problems, they are going to ask you to round in a particular way. So pay attention to how they ask you to round. This one says round up to the nearest whole animal. You can't have 0.09 of a wolf, and they want you to specifically round up. So what we should write here is 12,307 wolves, rounding up. So that means in the year 2018, they expect the total population of wolves to be 12,307. All right. Now let's scooch over to do part C and D of this problem. We're not quite done with this model yet. So I'm going to copy the model that we wrote down in part A. Part A was that future value of wolves was 7,100 e to the 0.055 t, where t equals 0 corresponds to 2008. That was the model that we built. So when I move to part C, I again have to interpret what it is it's asking. It says, how fast is the population growing? Based off of the wording, asking for how fast something is growing, we need to kind of put two and two together and think that this reminds us of a rate of change. How fast is something changing? How fast is it growing? How fast is it changing? So this can translate into it's asking about a rate of change, but then what does that mean? A rate of change we should associate with the derivative function. So it's asking about the derivative, and it's asking about that derivative rate of change at a specific time, 2018. And from part B, remember, we'd said 2018 was 10 years later, which corresponds to t equal 10. So what we have here, since it's asking for a rate of change in 2018, it's asking for a derivative at that corresponding t value. That means you're going to be plugging in 10. So my path is clear to me now. I should take the derivative of this function, my model there, and then when I'm done taking the derivative, plug in 10. You'll have the rate of change in wolves in 2018. So let's go ahead and get started. I want to find A prime. Now, from earlier sections, we know how to take the derivative of E. The derivative of E is itself times the derivative of its power. So the 7,100 stays there. The derivative of E is copy-paste, the same thing, but then you have to multiply by the derivative of the exponent. The derivative of 0.055t is 0.055. So you get this. I'm going to take 0.055 and multiply it by 7,100 and see what that equals. And I get 390.5. So my derivative function is 390.5 e to the 0.055t. Now this is my derivative function. This represents the rate of change in population at any time. But now I want to plug in t equal 10 into this derivative because I want to know the specific rate of change at 10. I have 390.5 e to the 0.055 times 10. And I get 676.835 and some change. Now, again, they will tell you how to round. So this time it does say round up to the nearest whole animal again. So when I plug in 10, if I round up, this gives me 677. Now, this is a rate. It's a rate of change. So this should have a rate of unit per unit time. So my model represent wolves, and the time they're talking about is years. So a rate of change would be 677 wolves per year. So the way we should interpret this is that in the year 2018, they added the rate of change was 607 wolves per year. So you can interpret that to mean that in 2018, 677 wolves were added to the population. So you might think that to be the wolf pups that were added for that year. And so this is how fast the population was changing. This was how much was added that particular year. Any year subsequent to that, that could change as wolves grow up and have their own pups and such. So that is to say that this isn't going to be constant year to year. That can fluctuate. But in the year 2018, that was the rate of change. 677 wolves per year were added at that time. Now, part D, we're using the same model up here. It says, in what year will the population be 21,330? So again, I have to kind of pick off what it is they're asking me to find. When they say in what year, they're asking me to find a time, how long it will take. And if they're asking about how long will it take for the population to be a certain thing, they're wanting you to find when A, the future value, will be 21,330. So that is to say, they want you to take your model here and fix your future value A to be this specific amount and solve for the T that would make that happen. So I want to plug A into this formula here, which in this case is 21,330. All right. We plugged A into my model there. Now I'm supposed to solve for T. And we should think here that the T is kind of stuck in the power on the E. So eventually I want to be able to get rid of that E so that I can have access to that T. But before I can get rid of that E, I've got to get the E by itself. So to get the E by itself, you should first divide both sides of this function by 7,100. So if you divide both sides by 7,100, over here on the right-hand side, you just have your E function by itself. And again, I want to get at the T, but the E is in the way. So I need to get rid of the E. And I can get rid of the E by introducing its inverse function on both sides. The inverse of E is the natural log. So I want to take the natural log of both sides. If you take the natural log of both sides, over here on the left, this is something you can punch on your calculator, but over here on the right, the ln and the E cancel, and you're left with what is in the power, 0.055t. Now at this point, you can get your t by itself by dividing both sides by 0.055. So then you have that t is whatever this punches out to be, ln of 21,330 divided by 7,100, and all of that is inside the log, and then that log itself is divided by 0.055. Let's go ahead and punch that out on our calculator, and that'll be how many years later the population will be 21,330. So I get 20.00035,906. Now, they will tell us how to round, and it says round to the nearest year. So I'm going to round that down to 20, and that's pretty close to 20 anyway. So we have that it takes 20 years for the wolf population to reach a population of 21,330. But even though this is a correct value for how many years later it will take, that's not the answer they want. They're not asking for how many years will it take. They want to know in what year will it be. So what they're asking for here is the calendar year. What is the year it will be? So remember, we started this keeping track at the year 2008. That's when they started keeping track of the wolf population. So if I'm talking about something that's 20 years later, that means the calendar year that this population number is reached would be 2028. That's the year 2028. That would be the answer. All right. So now we want to move on to number 2. But to do number 2, I need to take a detour and talk about a concept that I haven't quite discussed yet. Let's read it first. It says the decay rate for a radioactive isotope is 5.8% per year. Find the half-life of the isotope. So in order to find the half-life, I have to know what a half-life is. So for this, I'm going to go back over to my definitions on my page. If you're talking about exponential decay, the half-life is an amount of time. It's an amount of time that it takes for half of a material to decay. So if you let your model, in this case, a decay model, represent an amount of something, in this case, it would be an amount of a substance, then a half-life is a time t that it takes for 1/2 of that substance to decay away. So half-life is the amount of time it takes for half of the material to remain. Half of the material to decay means half of it remains. So let's take that idea over here. In order to answer this question, it says find the half-life. That means it wants you to find the time it takes for half of this radioactive isotope to decay. That means that I need to settle on a model. Now, because I'm talking about something decaying, I will use the exponential decay formula, CE to the minus KT instead of CE to the positive KT. And this one, I have to do a little bit of side work here to make a good argument on what to do with this. The problem with this setup is that if A represents a future amount of my radioactive isotope, future quantity of the isotope, and C represents the initial quantity of the isotope. The problem with both of that is that they didn't tell me how much of the isotope I started with. They didn't say I had 2 grams of the isotope or, 2 pounds or whatever. They said that it decays at a rate of 5.8% per year, and they wanted me to find how long it takes for half of it to be left. They didn't tell me how much I started with to know what half of that would be. So they kind of put me in a pickle here. I don't know what my initial amount was of my isotope, so there's no way for me to know what that future value would be. So I have to get a little tricky and clever with how I handle this formula. They did tell me K, at least. They said that the decay rate was 5.8% per year. So K, right here, is 0.058. But I don't know C, and I can't find A. What they ultimately want me to solve for is T. Remember, they want me to solve for the half-life, which is a time. But if I'm going to solve for time, they have to tell me what K, C, and A are, which I only know K. So what do I do about A and C? So this is where we have to get a little clever. I'm going to do some side thought process here. So if I'm looking at a half-life, it's a time for half of the material to remain. So if you let C represent the initial quantity of the isotope, then if a half-life has passed, that means they should have half of what I started with left, right? So if C is whatever initial quantity it was, then the future value that I will have after a half-life has passed is 1/2 times that initial quantity. So if C is the amount I started with, then after a half-life, I should have half of it left. My future value A is 1/2 of it. So this is where I kind of start plugging in this ratio. A is 1/2 of what I started with, and C is what I started with, whatever that was. And I just kind of go along with it. If you try to solve this for T, to solve for your half-life, nice things happen. What are you supposed to do when you solve an equation? You first get your E by itself, and I divide both sides by C. Here, C divided by C, that cancels. So you'd end up with 1/2 equals E to near negative 0.058T. This is an interesting place to make a comment. I'm ultimately going to solve for T, which means now I can take the natural log of both sides and carry on. But it's interesting to note that I have 1/2 sitting there. This 1/2 represents that half-life, 1/2. The ratio of future value to present value was 1/2. So this 1/2, or that is 0.5, if you were to punch it out, that represents the percent of material that remains. In this case, that's 0.5, or 50%. It's an interesting consequence that will come back later. So we're doing our algebra. We end up with a 1/2 over here because of the half-life thing. And we should note that this is no coincidence. The 1/2 is the percent, or that is 50% of the material that's still left, half of it. Now let's go ahead and solve for T as we were doing. I introduce a natural log on both sides to get rid of the E. The ln gets rid of the E, and I'm left with what's in the power there. Divide both sides by negative 0.058, and you can solve for your T by plugging this in your calculator. Make sure you're using your ln key and not the log key. So you have ln 0.5 divided by negative 0.058. And you get 11.95 and there's some change. Now look at how they told you to round. It says round to the nearest 1/10 of a year. So that means 1 decimal place. So I want to round to 1 decimal place, but it's already a 9. So it looks like the 5 would make that round up, which in turn makes the whole thing round up. So it looks like this one would be T is 12 years. So in this particular problem, it takes 12 years for half of my radioactive isotope to decay, and therefore for half of it to be left. Take 12 years for half of it to be left. All right, let's do a problem pretty similar to this one, a little bit different. Number 3 says bones from the skeleton of a prehistoric creature have lost 65% of their carbon-14. Note that for carbon-14, the constant of proportionality is approximately K equals 0.000124. Estimate the age of the bones, round to the nearest 1/10 of a year. So when you get down to what they're actually asking you to do, it says estimate the age. So that means they want you to find T. They want you to solve for T. Solve for T in which formula? Should I use the exponential growth model or the exponential decay model? Based off of the context of the problem, it says it's lost 65% of their carbon. That means I should be using the exponential decay model, CE to the minus KT. And, like before, they did give me the value of K here. And if they want you to find T, which is here, they have to give you values for K and C and A, all the other letters in the formula. But just like we had last time, they don't tell me how much carbon-14 was originally in the animal. So if A represents a future amount of carbon, and C was the initial amount, they didn't tell me how much carbon I started with. They didn't say there was, this many grams or moles or what have you of the carbon. So I don't know what my initial quantity was. If I'm going to solve for T, I need K and I need C and A. but they didn't tell me what C was, and therefore I can't figure out what A is. So this is where I have to get clever again and figure out how to get this. We have that. It says, the one thing it does tell me is that this creature has lost 65% of the carbon. Now that is a percentage, it's a ratio. And what I would really like to do is use the same trick that I used beforehand. So let me manipulate this equation. How is it that we usually solve for T? What's the first thing we do? We divide this constant away, no matter what it was, so that you get A over C equals e to the minus kt. And I had made this comment last time, but now is a really good time to mention it again. This fraction A divided by C represents the percent of material that remains. So let's think about this. If they tell me that my creature has lost 65% of the carbon, how much carbon does that mean is left in the creature? So if it's lost 65%, then 100 minus 65 is how much is still there, which is 35%. So this creature still has 35% of its carbon-14. That is a percent that I want to put in for this A divided by C fraction. A divided by C represents the percentage of material that remains, and I have the 35% of its left. The only thing is that you have to make sure that you put it in as a decimal, not as an actual percent. So A divided by C, change 35% to a decimal. A divided by C should be 0.35. And then I can plug in my K now and be on my way to solving for T, the time. So let's solve for T so that I know how old this creature is. Introduce natural log on both sides. The ln and the e cancel each other, and I'm left with the part that's in the power there. Divide both sides by this decimal, and you will have your T. And just make sure to round how they tell you. So T is ln of 0.35 divided by negative 0.000124. ln of 0.35. When we get that for T, let's round how they tell us. They say round to the nearest 10th of a year. So that means 1 decimal place. So that means my creature is 8,466.3 years old. All right. And that is the end of that problem. Now, here is a good place to stop the video, but I do want to comment that insofar, each of these problems I've been doing, I've had to first choose a model. Am I talking about exponential growth, which is that model? Or am I talking about exponential decay, which is this model? In each of these models that I've used so far, they've told me what K was. They told me what the decay or growth rate was. In the remaining problems in this section, they do not indicate what K is for these subsequent problems. And so we have to spend a little bit of energy figuring out what K is before we can start using the model to answer the actual question. So the problems that will follow in the next video, in order to build our equation, put it all together, they won't give me K. I've got to find it, and then I can put it in there, and then I can answer the question. All right, so stick around. I'll see you in the next video.